Okay, let's begin. Maybe you can share the screen.
Sure thing. Right, I think it should be visible.
Okay, so our next speaker is Amitayus Banik from Chungbuk National University, South Korea, and he's going to talk about discriminating dark matter environments through gravitational waves.
Okay, so hi everyone, and thanks Anish for this invite to present this work that I've been working on with some people here in Chungbuk National University. So with Jonghan Kim and his master student Junsung P, and with Yusin Tsai of University of Notre Dame. Let's jump right into it of what I'll talk about in the next 30 odd minutes or so. Firstly, I'll introduce first I'll motivate what we had in mind when we first started this project. Then I'll introduce the various topics that we are going to study. And firstly, we'll go for the various methods we'll need to look at this before we can attempt to distinguish dark matter environments from each other. So I'll talk first about how you can study binary inspirals with dark matter environments.
Hi, can you try to go full screen maybe if
it's not reading.
Okay. Then it should be fine.
Did it work?
Yeah, it works. It works. Yeah.
Okay, so we start again. Okay, so I just like to introduce briefly what we're going to be talking about for the next 30 odd minutes or so. I'll talk a bit about binary inspirals in dark matter environments. For that, we need to understand the environment itself. So I'll talk a bit about dark matter density profiles. Then I'll discuss how we use some simulation tools to actually study the merger of these black holes in dark matter environments. And then at the end of the day, what we were interested in was some gravitational wave observables. I'll talk in particular about the dephasing of gravitational waves. And based on that, we'll see whether we can actually discriminate or distinguish between different dark matter environments. And then I'll summarize what I've been talking about. So the general consensus is that we need dark matter. It should exist. Most of the evidence is gravitational. So in terms of studies of galactic rotation curves, gravitational lensing, and so on. But besides that, we don't know much about dark matter, especially since there have been null results from collider searches and indirect and dye detection searches. So that begs the question, in the worst case scenario, how do you probe dark matter if its interactions with the standard model are extremely weak or if they don't exist? Well, since the evidence is gravitational, one might want to look for gravitational probes of dark matter. And since we're in the gravitational era of gravitational wave astronomy, with upcoming experiments like LISA and the Einstein telescope, the most natural way to think about doing this is through gravitational waves. In particular, we're kind of interested in how gravitational waves are emitted from black holes with dark matter halos, as alluded to in the title. We're considering a specific kind of dark matter, so self-interacting dark matter, no portal to the standard model, just interactions amongst itself. This arises in some beyond the standard model scenarios. It also alleviates a bit of discrepancies that exist with cold dark matter and the standard model of cosmology, lambda CDM, on small scale structures. Probing SIDM properties through gravitational wave phenomena is not really new. Here's a very, very non-exhaustive list. So people have looked at like super radiant phenomena. So you have a spinning black hole, an enhancement of, so you have an enhancement of scalar particle production, which gets translated to the gravitational waves. And that can shed some light on these SIDM couplings. People have looked at dynamical friction and accretion effects of self-interacting dark matter on gravitational waves. Recently, there were, so these people here were studying SIDM halos around supermassive black holes and how that could kind of alleviate the so-called final parsec problem, and also give some gravitational wave signatures in the nanograv regime. In this work, what we're interested in is simulating these binary inspirals in dark matter environments. What we want to study is the dephasing of the gravitational waves because of environmental effects. And we ask the question, can you probe certain properties of SIDM by studying this dephasing phenomena? That brings me to the first part of the talk. Firstly, getting into the binary inspiral motion in these dark matter environments. So let's understand the environment itself first. Let's look at cold dark matter, CDM. Given the black hole masses, you have the total binary mass. There's a correspondence with the mass of the halo, the virial mass that it can support gravitationally. With that, you can determine the outermost regime of the density profile that's given by this NFW profile, where the parameters that are needed are this rho SC, the scaling density, and this RSC, the scaling radius. Given the mass of the halo, these are determined by so-called concentration mass parameter relations. And for example, in this work here, which is the one we use. Next, as you approach the black hole, the gravitational influence of the black hole redistributes the dark matter particles. It results in a spike formation. So you have this spike profile now. Here, the inputs are, you need information about the the amplitude, or this rho SP, and also the spike radius. There's also a spike index appearing that is subject to a lot of uncertainty based on how this spike is actually, constructed. We take in this work the spike index to be 7/3 for CDM, just because this gives the largest density profile, as we'll see later. You fix the other parameters by demanding continuity with the NFW profile, and the spike radius is fixed by requiring it to be the radius at which the mass enclosed by the original NFW profile is about, say, twice or some order 1 factor of the black hole binary mass. Now, let's go to self-interacting dark matter. There are self-interactions that should do something. So what the self-interactions do is they drive thermalization of the dark matter particles. Instead, now the NFW profile transitions to a core-like profile. You form a SIDM core, which you obtain by solving this Poisson-like equation, where V0 here is the dispersion velocity of the dark matter particles within the core. So the interaction information is basically contained in this V0. The core so this differential equation needs some boundary conditions to solve. You get the core density by demanding continuity with the NFW profile. You'd get the extent, which is the characteristic radius of the core, by this thermalization condition. So this, rephrasing it, it just says that you demand at least one scattering per lifetime of the core. And we parameterize this velocity average cross-section using this relation here. And for this work, we'll focus on the A = 0 or contact type interactions. From a field theory perspective, that corresponds to something like a lambda phi 4 coupling. And again, like in the CDM case, as you move closer again to the black hole, the core gets altered again. It becomes a spike-like profile again, but the spike index is a little different. It's given by this relation right here. And again, you get the amplitude by demanding continuity with the core profile. the spike radius for the SIDM case you get by demanding the dispersion velocity is approximately equal to the centripetal velocity at that point. And okay, sorry. Yeah, now that we know now we basically know what to do. So this is what the various density profiles look like. You can first see the black line is for CDM. And this, in comparison to the SIDM cases, it's about 10 orders of magnitude larger, the density itself. For the SIDM case, what we found is for a sigma over m less than 2 centimeters square per gram, no core formation takes place. So you basically continue NFW profile to a spike-like profile with self-interactions to some extent. Increasing the sigma over m, what that does is it expands the core. The net result is the central density, the rho zero, essentially starts reducing because your core has expanded. Good, we know how to get the environment. Now let's put this up to the in-spiral part by simulating a binary merger. So for the simulation, we used Kedju, which was recently, about, say, a year ago, became publicly available. This can incorporate post-Newtonian corrections to the orbit. We can calculate thus the gravitational wave emission at 3pn order. We choose a black hole binary with the following parameters. So you have the central mass, about 10 to the power 4 solar mass units. The second mass is about one solar mass unit, it's not about. And the mass ratio, as a result, is 10 to the power minus 4. We simulate the merger from 20 times the Schwarzschild radius all the way down to 8 times the Schwarzschild radius, where 8 times the Schwarzschild is defined as the merger point. This gives a merger time of about 1.4 years. And we chose this because this gives a frequency, gravitational wave frequency in the range 10 to the power minus 2, 10 to the power minus 1 hertz, which is in the sensitivity regime of LISA. And okay, the input we next need is the density profiles, which we did some work in the last section to calculate. So using the density profiles, we calculate the number distribution at each radius, where, so you integrate the profile, and then you divide out by this small MDM, which is the clump mass. So it's an n-body simulation. You can't really have an idealization of a particle. You have to input some kind of dark matter clump mass. We choose the clump mass such that the total number of particles is about, say, 1,000 to 2,000, so that we have enough statistics. It's rather straightforward to implement CDM in Kedju. There are specific classes for it. But SIDM is where things get interesting. You need to do something extra, which from what we understand, we're the first people to do this for now. What we did is we adopted a Monte Carlo algorithm based on this work here. Roughly, this is the probability, and you have some input parameters such as the density, the sigma over, again, the interaction strength, the relative velocity, the time step, and this theta function. What that does is enforces energy momentum conservation. So the algorithm is as follows. Within a certain distance, you find some neighboring dark matter clumps. The interaction occurs if, when you calculate the probability, this exceeds a randomly assigned weight. You calculate the kinematics after the scattering in the center of mass frame, and you have the condition at that given time step, these clumps cannot interact again. So that's the algorithm in a nutshell. We implement this at every time step of the binary evolution. So Kedju solves the equations of motions for the orbit. At the same time, this algorithm is implemented to study what happens to dark matter and how it impacts the black hole, dynamics as well. We simulated a range of interaction strengths. And embarrassingly here, I could not embed a movie in LaTeX, so we have to do this the old-fashioned way, in which I share my screen here. So I give here two interaction strengths. And so the density profiles, as we saw, would be the same because it's less than 2. So it's 1 centimeter square, 0.1 centimeter square. The central density would be the same. The only difference is is the interaction strength. And if I let these play now, you can see within a couple of time steps, in the lower interaction case, the dark matter particles are essentially ejected out, whereas in the larger interaction case, they can stay around and constitute and affect the merger dynamics of the binary. The reason they get injected out is simple. It's because you have a shrinking orbit. This releases some orbital energy when it shrinks from one radius to another. And this is distributed to the dark matter particles. And okay, so after some point, you can see everything gets kicked out. And maybe we, go towards the end of the merger where you can see a couple of particles can stay around. And let's see the results for the sigma over m that we simulated. Sorry, I'm having a bit of difficulty tiling got it. So you can see for so let's start with the left-hand plot. We have the various initial density profiles that we gave as input. The CDM is just on a larger, occupies larger radii, just because of the fact that there's a lot of, the density is just much, much higher. So you need more particles to distribute. And the SIDM essentially we found could be confined here. We let this run so on the right-hand plot, I show you the results after 1 year of simulation time. And you can clearly see the central density for CDM is disrupted. By disrupted, it means that most of the particles are kicked out. They occupy the larger radius area. And for the SIDM, most of the particles can actually stay inside and help affect the merger dynamics of the binary, as I showed you in that movie for a couple of cross sections. This maintaining of its central density is kind of similar to this this hypothesis that these guys had in this SIDM halo with supermassive black holes paper, where there was a kind of refilling process. This is not really a refilling. It's more like these particles can take the orbital energy and not get disrupted. So they can stay around and affect the binary dynamics. We computed next the scattering events. We had a look at the scattering events. In our simulation, on the left plot, I show you the number of scattering events that we had over the course of the merger. You can see the peak kind of maximizes, so you get the maximum number of scattering events at sigma over m equal to 2. In comparison, on the right-hand side, you have the scattering rate. That's just a naive estimate just by comparing the sigma over m times the rho times the v. The v does not change so much. It's about order 0.1 or 0.01 C. Sorry. So you can see here, if you just compare the scattering rate versus the sigma over m, this is maximized at some cross-section equal to 2, which is reflected also in this number of scattering events. And this is kind of like an optimum value. It's optimum because it maximizes, one, the density of the particles. Second, it's that cross-section that can, you can have enough particles around to assist and maximize the boundary. And what we predict is that this is independent of the black hole binary masses. What I mean is independent as I mentioned earlier, when you have the black hole binary mass, you fix the entire mass of the halo. Just choosing a larger black hole binary mass will, of course, increase the mass of the entire halo, but that's just a scaling effect. The scattering rate and all is determined by the SIDM dynamics. So of course, if you increase the mass, the rho might reduce. As you can see, I take the hypothesized case of which you have Q equal to 1. Here you can see there's a drop just because the density is lower in that case. But nevertheless, this maxima, this optimum value should still occur at around sigma over m equal to 2. We're currently checking for a different mass ratio to see whether this is the case, and we're fairly confident this should work out. Now the question is, okay, this is nice and all to see. We observe some features. Can you actually see this in, say, gravitational wave observables, as I had advertised? So to know whether this can happen, let's first understand how this binary merges. Let's talk a bit about the power losses in the system. For the vacuum case, this occurs due to power losses due to gravitational wave emission, which scales in this famous Peters formula as such. If there's an environment, there's additional dynamical friction, which scales proportional to the density of the halo. So naively, you'd expect if the halo is larger, you would have a much more larger power loss in dynamical friction. Let's quantify the merging time using this number of cycles that are accumulated over the merger, this n cycle. It's just counting, it's physically just counting how many times the binary keeps orbiting around until it merges. And we can quantify thus this dephasing effect by the difference with the environment, the lesser number of n cycles accumulated in environment with respect to vacuum. This is greater than 0 because the environment has additional power losses. Therefore, you merge faster, and therefore the delta n cycle is always positive. For CDM, we found this delta n cycle to be of the order of 10 to the power 4. If you naively estimate this should be much larger, but you have to take into account the disruption of the spike profile, as I'd shown you in the plot a few pages ago. What happens for SIDM? You can see that it's of the order of 10 to the power 3, an order of magnitude less than CDM. So that's already a little surprising because I've shown you the density profiles for SIDM versus CDM. There's a difference of about 10 orders of magnitude. Despite that difference, you can still end up with a finite and appreciable with respect to CDM dephasing effect. The main reason is that your SIDM spike does not get disrupted. Therefore, like I said, these SIDM particles stay around and assist in the merger of the binary, and hence it's a kind of accumulated dephasing effect over the merger period. And you can see here for the n cycles, there's a kind of maxima behavior. In our simulation, just by calculating the values, this was at 1. We could not really, we had to run a finite set of sigma over m. So you can take this graph with a pinch of salt. But as I'd shown you in the slides a couple of times ago, sigma over m equal to 2 is kind of like the magic number. So if you include more points between 1 and 2, I would expect this to shift somewhere, this peak to shift somewhere to the right. But it's good at least that you can see some kind of imprints of what we observed in the simulation on this delta n cycle. And one thing to note is that these values are kind of small. So now comes the question, can you tell different sigma over m apart? So firstly, the questions one would want to ask is, can you differentiate between vacuum and environment? Can you differentiate between CDM and SIDM? And can you differentiate between SIDM at various cross sections? To first answer that, you need to know what LISA can do. So the question one would need to ask is, given that LISA detects a gravitational wave signal, what are the uncertainties on the measurement of that signal? To do this, to get an idea of this, we use GWFish to forecast the detector uncertainties. So GWFish is a publicly available code, which recently incorporated LISA in its detector set. It simulates the detector response using a Fisher matrix analysis for a given signal to noise ratio. What it employs is fitting various vacuum approximates to the signal. But the vacuum approximates or the vacuum waveform, once you fixed your time to merger, it's completely characterized by the so-called chirp mass. And therefore, the only thing that you need to understand is the uncertainty on the chirp mass to find out whether you can, what's the uncertainty on the chirp mass to find out whether you can, okay, do you see the signal? What's the uncertainty on the chirp mass for that associated with that signal? So this we simulated using GWFish. Next, let's go to dephasing. The dephasing is essentially a shift in the n cycles. Now, if you work with the vacuum template, a shift which is determined by the chirp mass for a fixed merger time. This means a shift in the n cycles corresponds essentially to a shift in the chirp mass. What we do is we take the vacuum template, which is kind of well understood. We take the vacuum template and shift it by some value delta m chirp and fit this to the environmental waveform and to calculate this delta m chirp. This gives you, so this tells you how much the signal needs to shift to match the environmental waveform. We can go one step further. After you calculate these shifts to the environments, you can shift your vacuum template by an environmental shift. Call that the quote unquote environmental template and use that to compare to another environment and calculate the shift accordingly. Now, the main point is, if any of these shifts is larger than the detector uncertainty, LISA can distinguish these signals. And let's see for a couple of values for vacuum versus environment. So on the left table, that's the detector uncertainty, that's the uncertainties on the chirp mass for LISA for various signal to noise ratios. And you can see it's at the order of 10 to the power minus 5 in the most, say, conservative or modest estimate of SNR equal to 15. And on the right-hand side, you can see the shifts that we calculated by taking the vacuum template and trying to fit to various environments. So immediately, just by the numbers, you can see that LISA can at least distinguish between vacuum and various sigma over m. Further, sorry, not various sigma over m. It can differentiate between at least CDM and SIDM. We further noted that it could differentiate between CDM. So if you shift first to CDM and then calculate the shifts for sigma over m, we can find that indeed you can differentiate between CDM and SIDM. Now we come to a point which was a little we were not sure about. Can you differentiate between various SIDM sigma over m? It turns out you can. So on the y-axis, I give you the various uncertainties associated with when you shift first, you first shift to the sigma over m equal to 0.1, and then you try to fit various sigma over m. These are the calculated shifts, just from environment to environment. And these colored lines are the uncertainties on the chirp mass from LISA at various SNRs. And you can see that at SNR 15, it still might be possible, though it's a little contentious, say. But at, say, a bit, if you're willing to relax the value of the SNR, take it a little higher, stay SNR 40 as is commonly done, you can indeed distinguish between various sigma over m. So as I promised that, yes, it might be indeed possible, given dephasing of a signal, you can distinguish various properties, namely the self-interaction strength of SIDM, just by studying the dephasing of gravitational waves. So to summarize, we simulated binary mergers with SIDM and CDM environments. The SIDM simulation to obtain gravitational wave observables, we believe, is the first ever one done yet. In our simulation, we observed some nice features, such as the CDM spike profile gets disrupted because of the orbital energy release from the shrinking binary. We also observed the effect of self-interactions in maintaining the central density for SIDM. Next, we predicted an optimum sigma over m for which balance the density and also the interaction strength. And this we found was reflected in the dephasing of the gravitational waveform in the delta n cycle. And based on these dephasing effects, we looked at whether LISA could distinguish between vacuum and environmental signals, and also for various environmental signals. And indeed, we found that, yes, this dephasing effect can shed some light on if dark matter is self-interacting. Yep, we can gain insight of its properties. So with that, I come to the end of my talk, and I would like to thank you all for listening, and thanks again for the opportunity.